the grade 10, if you still remember, when we talk about the ideal gas law, các bạn còn nhớ cái định luật khí lý tưởng đó, khi các bạn học ở lớp 10 đó, PV bằng nRT. Còn bạn nào nhớ không? Bạn Khánh Ly còn nhớ không? So PV equal nRT. This is the first law. I'm sorry, this is the ideal gas law. So in this part, we should be able to apply the ideal gas law. Okay. We should also apply the relationship between the pressure, the temperature, the kinetic energy, and the speed of molecules. So here we try to relate the macroscopic properties. So we have pressure, temperature, and so on, to microscopic properties, speed of molecules, kinetic energy, so on. And we define and also apply the relationship between the mean free path. So we are going to study to know what is the mean free path to the diameter of molecules and also the number of molecules per unit volume. So we are going to study the relationship between them. And we apply the Molar specific heats, of adiabatic expansion of an ideal gas. So this is the part where we once again study things related to the specific heat. Okay, what we've seen in the first part. Các bạn thấy tôi chuyển slide chưa?
Yes.
Yeah.
Okay, so let's go to the introduction. Then, what is the kinetic theory of gases? Here I have a figure for you to better imagine. We can consider the gas as just a point, just a dot in the space, and normally the gas is confined in a certain volume. And what we are going to study is that we study the behavior of gases that relates the motion of atoms. So I mean a microscopic property to macroscopic properties of the gas, such as the volume, the temperature, the pressure. So this is the key idea of the kinetic theory of gases. And this kinetic theory of gases is based on several assumptions, because here we do not talk about real gases. We talk about an ideal gases. Then this kinetic theory follows several assumptions. Firstly, the gas consists of very small particles. Okay, very small particles, just like a dot, như một cái chấm, như một chất điểm thôi. And the particles have the same mass. So no matter what the gas particle, hydrogen or oxygen and so on, they have the same mass. This is our assumption, okay? In reality, actually it's different. Then the number of particles is so large that we can apply the statistics. Yeah, we can apply the statistics. And this one is important. All collisions are perfectly elastic. I think we learned during the first part of this subject, fundamental physics, what an elastic collision is, right? So a collision that after that the energy is conserved. So I mean the total energy, total kinetic energy of the system is conserved. So we have an elastic collision. Cái này phần này thì các bạn học ở trong cái phần mechanic rồi. Va chạm đàn hồi đúng không ạ? Cái động năng của nó được bảo toàn sau va chạm đó thì ta gọi là va chạm đàn hồi. And finally, except during the collisions, the interactions among molecules are negligible. So we consider that there's only interactions when the molecules collide to each other. So there's no forces, right? No forces. Then no interaction when they do not collide. But in reality, it's different, okay? Is it clear here? So please remember several assumptions of the kinetic theory of gases. Of course, this kinetic theory of gases have a lot of applications. For example, we can study the combustion of fuel, okay, in our motors, our cars, and so on. We understand how does it work. Yeah, we explain it based on the kinetic theory of gases. So these are some more examples of, for example, the production rate of the fermentation gas. Okay, when we bake the bread, or we explain how the heat exchanges between the oceans and the atmosphere can affect the weather conditions, etc. So these are some applications. We use the kinetic theory of gases to explain phenomena of things. Try to explain how does it work and so on. In the kinetic theory of gases, we will study 4 main relationships. Firstly, the relationship between the pressure and kinetic energy. Secondly, the temperature and kinetic energy, and then the collision with container, and the speeds of molecules. We are going to study different types of speeds of molecules in this part. Is it clear until here? If things are not clear, so please, you can stop me anytime, okay? I can explain once again. Good. So now we try to remind you the very simple definition. What is 1 mole? Actually, for example, in chemistry, you talk lots about mole, but what is the definition of 1 mole? Someone knows? 1 mole là gì ạ?
1 mole is consists of 6.022 tức là 1 mol thì gồm có 6,022 nhân với 23 phân tử hoặc nguyên tử.
Good. Thank you. Next time try to explain it in English, but you are totally right. Actually, this is the new, let's say the new definition of 1 mole. Actually, for the old definition, 1 mole is the number of atoms contained in a 12-gram sample of carbon-12. Okay, so this is the old definition. Actually, now we use the, let's say, the new definition. We define exactly that 1 mole contains 6.022 so on times 10 to the power 23 atoms. I mean elementary entities. And we know that this number has a name, right? Yeah. So the Avogadro's constant. So it has a name. The Avogadro's constant. And this is what Avogadro said he said that all gases occupying the same volume under the same conditions of temperature and pressure will contain the same number of atoms or molecules. Okay, so no matter what the gas is, if they occupy the same volume, if the conditions of temperature and pressure are the same, then they have the same number of atoms or molecules. Okay, so these simplify a lot of things here. Now, we study the relationship between the number of moles and the number of molecules and the number of molar how to say the number of molecules in 1 mole. This one is also to remind you, I think you used a lot of this formula in chemistry already, right?
Yes.
Yeah, so just remember here the definition, not really the definition, the notation. For example, the small n is actually the number of moles. The big N is the number of molecules. And the Na is the number of molecules in 1 mole. Okay. And the number of moles can also be calculated using the mass. Okay. We have the M-SAM here is the mass of the sample, our gas sample. We know the mass of our gas sample. The big M here stands for the molar mass. So the molar mass, okay, actually this is the mass of 1 mole. Then the small m is the molecular mass, but you should understand that. Do not make mistake. When you see a lot of n here or a lot of m here, sometimes you make mistake of what is the big M, what is the small m, what is the mass of the sample, and so on. Okay, please be very careful here. This is simple, but do not make mistake. Khi mà chúng ta cứ nhìn thấy quá nhiều chữ N, quá nhiều chữ M, đôi khi chúng ta bị lẫn. Okay. One of the very important parts of the kinetic theory of gases is the ideal gas law. The ideal gas law. Actually, the goal of the ideal gas law, this one you already learned during the 10th grade. Okay. Bạn học ở lớp 10 rồi đó. The goal is to explain the macroscopic properties of a gas in terms of the behavior of the molecules that make it up. So we try to relate the macroscopic properties and the microscopic properties. Then what we see is that if we confine 1 mole samples of no matter what gas is in the boxes of identical volume and temperature, then we see that the measured pressure are almost the same. And at lower densities, the differences tend to disappear. Actually, if you look at this figure, we are talking about the ideal gas and the real gas. Ideal gas is based on the assumption that I already gave you in previous slides. Okay, the real gas, but you see the characteristics of real gas are different. For example, the particles, they will have volume, they will have energy lost in collisions. So the collisions are not elastic, but inelastic. And then there are also forces between the molecules. But however, these behaviors tend to disappear at very high temperatures and very low pressure or very low density. Okay, densities or pressures here is the same. Then we find mostly the same thing. Therefore, the ideal gas concept will allow to gain insights into the limiting behavior of real gases. So instead of studying the real gases, we can study the ideal gas, and then we can already have good ideas about the limitation of the real gas. Good. And this is the formula of the ideal gas. Okay, PV equal nRT. The ideal gas has another name, which is general gas equation. And this is this one, PV equal nRT. So P is the absolute pressure. Remember, this is the absolute pressure, not the gauge pressure. Okay. We know that the absolute pressure and the gauge pressure has a difference of 1 bar, 1 atmosphere. Okay. The gauge pressure là cái áp suất mà các bạn đo trong đồng hồ đó, và cái áp suất tuyệt đối thì cái áp suất mà các bạn đọc ở trong các cái đồng hồ đo áp suất, các bạn phải cộng thêm cái áp suất khí quyển vào thì nó mới trở thành absolute pressure, đúng không? Mới thành áp suất tuyệt đối. And we know it already. The temperature should be measured in Kelvin. Do not make mistake, okay? Last time I saw a lot of people, a lot of students, when they calculate the pressure or the volume, for example, using the ideal gas law, they did it wrongly because they used the temperature in degrees Celsius and not Kelvins. So you should convert it. The R here, the R is actually the ideal gas constant, or also called the universal gas constant.
Professor, can I ask what units do we use to calculate the absolute pressure?
I will tell you in the next slide. Okay.
Okay.
Yep. Because it relates to this question, the units of the gas constant. Remember last time when I talked about the dimension, yeah? So in your equation, the part from your left should have the same dimension as the part from your right. Then here for the gas constant, you may see that even we call it a gas constant, it has different values. Why? Because you can consider different units. For example, here, if we measure the pressure, okay, in atmosphere, the volume in liters, of course, the mole in mole, and the temperature in Kelvin. We will have this value for the R gas constant, the R. Okay. Remember, 0.08 is the value that I think you use quite a lot during high school. Yeah, and the unit is liter atmosphere per mole Kelvins. But for the SI unit, actually we use this. joule per mole Kelvin, and the value is 8.3 something. So this is the SI unit, and I think you are going to see this value much more than this value from now on, because we are going to use the SI unit. You can write it in this form also when, for example, the volume is measured in cubic meter. The pressure is measured in Pascal, Pascal, and the moles is measured in mole and temperature in kelvins. Okay, these are two SI units that I think you should remember. So please do not just remember the numerical value. You should also remember the units. The units is important. Okay, the unit. Good. We can rewrite the ideal gas law based on the Bosman constant. Actually, we define the Bosman constant as the ratio between the gas constant and the number of Avogadro constant. Xin phép các bạn, họ đang lau kính cho nên nó hơi ồn, nó cứ như đập vào tai bộp bộp ấy. So, đấy. Bước cả vào đây nữa. Chữ khó tí nhé. Okay, so the Bosman constant is this one. Please also remember we are going to use it. 1.38 times 10 to the power minus 23 joule per Kelvin. So this is the value of the Bosman constant. Okay. Now, I have an example that we can use the ideal gas law to explain. Xin phép các bạn. Okay. What we have is that we have a stainless steel tank, and this tank is filled with steam. Okay, with steam. We know that steam, for the water to become steam, it should has temperature starting from 100 degrees Celsius. Okay, and this is what happens when we pour the water onto the tank to rapidly cool it. So the tank was crushed very quickly. Actually, we can use the ideal gas law to explain this accident. Okay, we can use the ideal gas law. Remember that the ideal gas law is written as PV equal nRT. Then what we have is that the volume is constant, right? The volume of this tank is actually a constant. The number of mole is also constant. The number of mole is constant. And the gas constant we have. So I mean the N, R, and V are constant. Now, what is changed is just the temperature, okay? Before we have a very high temperature, after that we have a very low temperature. Then what will happen? What will happen? When we lower the temperature, actually we lower the pressure, right? PV equal nRT. So V constant, N constant, R constant, then the higher the temperature is, the higher the pressure is, and vice versa. Now, when we rapidly cool it, we also decrease the pressure inside of this volume. Okay, we also decrease the pressure inside. Then what will happen? The pressure inside of the this tank is too low, while the pressure outside of this tank is equal to the atmospheric pressure. And because of the difference in the pressure is too high, then it was the atmospheric pressure that crushes, that crushes this tank. Okay. So this is one example, typical example that we can use the ideal gas law to calculate, to explain phenomena that we see in real life. Now, what is the work done by an ideal gas law? Okay. Last time we saw that this formula is always true. It's true for any cases, any process. The total work done by any process equal the integral of PDV. So we use it when we know the change of the volume. Okay. Now, if we apply for the case of an ideal gas, we try to do it together. We replace the expression of the pressure to this formula. Okay, please follow the mouse. Các bạn theo dấu con chuột của tôi nhé. Then we have this expression. This is what we have. Okay, because nRT here is actually a constant, we take it out from the integral. This becomes solving this integral. And if you apply a little bit of mathematics, you should be able to solve it easily. This is actually this one. Okay, this one. And finally, the work done by an ideal gas at constant temperature. This one is constant temperature here, okay? Could be written as this one. So the total work equal nRT ln of VF over VI. So this is the work done by an isothermal expansion or compression. Okay, at constant temperature we have this, at constant volume and at constant pressure. What do we have? At constant volume, this one we started already. Since the system does not expand or compress, then there's no work done. Okay, no work done by the gas if there's no change in volume. If you do not remember it, you can even use the general formula here. So you see VI and VF is the same. So this one should be 0, right? So this is for constant volume or so-called isochoric process. If we consider an isobaric process, I mean at constant volume. I'm sorry, at constant. Here I did a mistake, okay? I rectify it. Constant pressure. Pressure luôn thì chứ không lại pressure. Constant pressure. This is what we have. This one we learned also during the last part. At constant pressure. Then if we replace it into the general formula, I mean the integral, we can take the pressure out from the integral, right? So the work done by an ideal gas law is simplify the product between the pressure and the change in volume. Do you see the slide?
We see, but you didn't put full screen.
Yeah, and now do you see it in full screen?
No.
No.
Okay, I redo it. Is it in full screen already?
Yes.
Okay, thank you. Okay, so you remember the work done by an ideal gas law, ideal gas at constant temperature, constant volume, and constant pressure. Okay. Now I give you 5 minutes or less to calculate it. Yeah, try to do it by yourself very quickly. Good. So here, this is the way we solve it. This one is simple. Okay. Now we can apply the ideal gas law. Here, you just have to remember that the unit, okay, the unit, you can express the pressure in atmosphere or Pascal. Is up to you. You can express this one, the volume in liters or cubic meters, is up to you. Because you see when we apply it, this will be gone. The volume will be gone. Good. The pressure, if you leave it in atmosphere, then you can find finally in atmosphere. But the temperature, you should convert it in kelvins. Like I said, a lot of people make mistake here when they do not convert to kelvins. And if you do the calculations, it will be very wrong. Okay. Now I have another exercise. We have 1 mole of oxygen. We assume that our gas is ideal. This 1 mole expands at a constant temperature, from an initial volume to a final volume. First, we need to establish the PV diagram. Okay, the PV diagram is very useful for us to solve questions related to the gas. Then we have to calculate the work done by the gas during the expansion. Okay. How to establish the PV diagram? How to establish it? This is what we have. So remember that the volume diagram is the diagram that relates the pressure and the volume of the process. If we apply the PV equal nRT, okay, at constant temperature, we have the value for temperature. We have 1 mole, so the N, we have the R. Then for each volume, we could have a pressure. Each volume, we could calculate a pressure. For example, here we have 12 here. You should be able to find the pressure of around here. And for final volume, so 19, you could find something here. Okay. If you take some more values, you can see that the constant pressure process in the PV diagram is actually a curve. It's not linear, actually, it's a curve. Okay, so this is the way we establish the PV diagram. To calculate the work done by the gas during the expansion, we know that this is a constant temperature expansion. Then we apply the formula that we have developed together. Okay. And remember here, it is measured in Kelvin. Here, the volume, it is measured in liters. Okay. And you use the R, the gas constant. With this value, you should be able to find the final result. Please do not make mistake. That's why I say that each time when you write a value, please also write down. Please also write down the unit associated with this value. What we want to find is the work. Actually, the unit of work is joule. Am I right? Joule. Then we use this value for R. Then you see that 1 mole and 1 mole here is gone. Kelvin and Kelvin here is gone. Okay, here we do not need to pay attention. Then we have the joule left here, joule and joule here. Good. Is it okay until here for the ideal gas law? PV equal nRT. Now, let's move. Now we consider the next aspect of the kinetic theory of gases. We consider the relationship between pressure, temperature, and root mean square speed. I will explain what is the root mean square speed. But before, let's say our problem. Let's see our problem. We have now. Let's consider that we have n moles of an ideal gas. Firstly, and these n moles are contained in a cubical box. Here, this is the cubical box. And this box has edge length L. Okay. This box has edge length L. The mass of each molecule, each gas is m, and each gas has a speed. Okay, has a speed. What we consider for the time being is that all collisions of molecules are elastic. And for now, okay, for now we consider only the collisions of the molecules with the walls here, this shaded wall. So to develop the relationship between the pressure, temperature, and the speed, we do step by step. Firstly, we consider the movement of only one particle. One particle, okay? Yeah. Now, if we consider this particle, and we consider only the component of movement along x-axis, along the x-axis. Is it okay? What do we have? Let's imagine this molecule will move and will go along the x-axis and will collide with the wall. And because this is an elastic collision, okay? Elastic collision after colliding to the wall, what will happen? What will happen?
It would bounce back.
It will bounce back with the same kinetic energy. Okay, do you agree with me? Because this is the elastic collision. Then, if we write the formula to calculate the momentums, the particle's momentum. This one you already learned during the first part, during the mechanics, right? If we write the formula for the particle's momentum along the x-axis, what do we have? We have the change in the momentums equal this one. This one is the final momentum. After this collides to the wall, it will be bounced back. And if we consider also the direction, it will have a minus. Cái này bị lỗi các bạn nhé, x là cái x bé này nhé. Để tôi viết lại. Chờ tôi một tí. Cái này là vận tốc theo phương x. Viết như thế này. Bởi vì viết trong Word nó tới lúc xếp đi xếp lại nó có bị nổi lên. Okay, so this is the final momentum. So we have a.
Teacher, you haven't shared your screen yet.
Okay, I'm sorry. Do you see it?
Yes, but it hasn't it hasn't been in full screen yet.
Is it okay now? Not yet?
Not yet.
Not yet.
Okay, not yet. I think now it's okay, right?
Yep.
So this is the final momentum. We still have mv. Okay. And this is the initial momentum. So the change is actually the final momentum minus the initial momentum. So finally we have minus 2mv. This is the momentum along the x-axis. Do you agree with me? You have to write it down, okay? Các bạn ghi ra giấy đi, so we can continue. Then here, the momentum delivered to the wall by the molecules during the collision is 2mv. Here, the momentum delivered to the wall by the molecule is 2mv. Now, if we consider the time also between the collisions, we call it delta T. Okay, this is the time actually for this molecule to travel from this wall, okay, from the opposite wall to this one, to this shaded wall, and then back again. Then we have a distance of 2L. We have the same speed v, okay, vx. We still consider the speed along x-axis. And if we consider the time delta t, what do we have? We have this one, okay? The time is actually the distance divided by the speed. Then we continue. If we want to calculate the average rate at which the momentum is delivered to the shaded wall by this single molecule, okay, the average rate at which momentum is delivered to the shaded wall, then we take the delta P along the x-axis divided by the delta T. Okay, finally we have this one. Please write it down. Các bạn viết ra một tờ giấy, viết tất cả ra một tờ giấy nhé. Is it okay? This is the average rate at which the momentum is delivered to the shaded wall. What else? If we apply the second law, so we know that the second law says that the force is actually the pressure, okay, over time t. Actually, we can have another expression, another relationship. The pressure, this is for the force, okay? And this is for the pressure. The pressure is actually the total force of all molecules of different speeds, right, applied to an area. So the ratio between the force per area will give us the pressure. Do you remember? Here, if we consider in this case, what do we have? We have the area, is this one. So L squared. The F is this one, the momentum. I'm sorry, here's the momentum divided by the time. And if we rewrite it, we can write like this. So this is for the F of all molecules. So this is the molecule 1, this is molecule 2, this is molecule 3, and so on. Okay, so this is the force number 1. This is actually the momentum divided by L, and so on. Okay, here I show you once again. P over T, we have this one. Okay, this one is actually the force. Then we just replace the force with this expression. Then all the forces, we write it down. So we have the total of all forces applied on an area. So this area, we have the pressure. Here I apply only the mechanics, okay? If we rewrite it, we can have this one.
Teacher, I do have a question.
Yes.
So in the previous slide, why do delta px doesn't have
Yeah, this one. This is delta P, and we consider along only the x-axis.
so why doesn't it has a minus sign as we, because in the previous slide you
Here actually we consider the change in the particle momentum, okay, the change. But for the total momentum delivered to the wall during the collision, actually this one.
So you mean it is the absolute value?
But no, actually, how to say? Because the momentum, because we consider the direction, okay? We consider the direction along the x-axis. It is bouncing here and then bouncing back, then it will have this change.
I mean,
but
I mean,
if
this slide is delta px is has the minus sign, but the next slide doesn't have the minus sign.
No, actually here, when we consider the change, then the momentum will have a minus point. When we consider the change, because we consider the direction. But here, this is when we consider the magnitude, okay? Một cái là thay đổi của momentum. Thì khi mình tính tới hướng thì nó là trừ 2mvx, nhưng mà đây mình tính tới độ lớn.
Rồi ạ, ok.
Ok, mình tính tới độ lớn. Ok, I continue. mình đang lập luận nhé, cái phần trên các bạn chưa quan tâm lắm đâu, mình đang lập luận là vì sao mình có cái độ lớn là 2mvx này cho cái momentum của cái thằng molecule này trong cái collision nhé. Now I continue. We have this one. Okay, after when we developed. Cái này là VX1 nhé, cộng VX2 vân vân. Cái này tôi nhầm này, không phải VX12 đâu, VX1 cộng VX2 vân 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 đó. And if we rewrite it, we replace the number n here, actually here, okay, the number n, the number of molecules by the Na, and also this by the average speed. We will define this average speed later on. But for now, we consider, xin phép các em tí, cái này nó cứ bị lỗi ở cái phần khi mà tôi sử dụng cái PowerPoint này, nó là MV bình nhé. Cái số 2 nó cứ bị hạ xuống cùng với cái số 1 thì tôi viết lại chứ không các em lại bị chép nhầm. MV bình chia L, mình đang nói tới momentum mà. Nhưng mà khi mà viết ở cái Word này nó cứ bị tự thay đổi. Viết ở cái PowerPoint này nó tự thay đổi. Tôi viết lại ở đây để cho các em tránh bị nhầm. Rồi, nhìn lại để tránh bị nhầm nhé. Các bạn thấy, đợi tôi tí để tôi share lại screen. Các bạn thấy screen chưa?
Được.
Okay, here mv squared, okay. Now if we continue, if we replace all of these, okay, here we have
Teacher,
the
not full, the slide is not full screen.
Vẫn chưa full screen à? Is it okay?
Yes.
So we replace the big N here to the Na, the number of mole times the constant, Avogadro's constant. Okay, one step. The second step, here we just take the average. Okay, when we take it out, we will have an average that we will define later. We will define it later. We continue. We replace once again to the pressure to calculate the pressure. Okay, once we already define this one, we replace this one. Then we will have the pressure that can be written like this with a new term that we will define. Okay, the V average squared here we will define. If we replace once again the M and A here to the M, this is actually the molar mass, and the L3 here, the cubic L here, but this is actually the volume, right? And we rewrite the pressure. We will have this expression. Now we already relate the pressure and a kind of speed. The pressure and the speed of the molecule along the x-axis, okay? Then for any molecules, what do we have? We know that the molecule does not move only along the x-axis, right? But the molecules are moving in random directions in x-axis, y-axis, z-axis. Then we should have this one. We should consider that the x-axis is only 1/3, one component of the movement of the molecule, and it is equal only 1/3, yeah, of the final speed squared of the molecule. Okay, we should consider this one. Then we can rewrite the pressure, yeah, the total pressure applied on the wall, any wall, yeah, in any direction, like this one. Okay, do you still follow me? If you follow me until here, now we define the root mean square of the average speed. This one, the average speed squared. We call it the root mean square speed. We will see that the normal average speed will be very different than the root mean square speed in the very simple exercise that I give you in the next slide. Here, once we call it the root mean square speed. So I mean the average upon the sum of the speed squared. We call it, and then we take the root mean square. We have the root mean square speed. Căn của tổng các cái vận tốc, nhưng mỗi vận tốc này nó đã được bình phương rồi. Okay, then we have this one. Is it okay? If we combine once again with the ideal gas, what do we have? We can calculate the root mean square speed, yeah, which is this one. PV here equal nRT, so you replace it. Then the root mean square speed can be calculated using this formula. Okay, now this expression will tell us how the pressure of the gas depends on the speed of the molecules. So the pressure is a pure macroscopic quantity, okay? And the speed of the molecules, one kind of speed of molecules, this is actually a pure macroscopic quantity. When we consider the root mean square speed, we know that this is only a kind of average speed. We will study in the next slide that there are all the average speeds of the molecules that we can consider also. To differentiate between a normal average value and the root mean square value, we can solve this exercise. Here we have 5 numbers. 5 numbers, okay? The normal, let's say the normal average value is this one, right? The normal value is this one. So the total of all the values divided to the number, to the quantity of the value. Here we have 5 values, we divide by 5. But the root mean square value is different. We have to square each value. So we divide by to the number of values. And then we take the root mean square. And it will give us this one. Okay, the difference between the average value and the root mean square value. So is it okay until here? Now I remind you once again, please remember this formula and this formula. We will continue to study another speeds, but for now, please remember the relationship between the pressure and the root mean square speed. Actually, you can just have to remember this one. But how to find this one, I have to show you that we base totally on the kinetic, on the mechanics, on the movements of the molecules to establish the relationship between the pressure and the speed. Yeah. Các bạn chỉ cần nhớ cái formula này thôi. Tuy nhiên là tôi vẫn phải chứng minh cho các bạn là cái formula này nó từ đâu ra. And you remember the expression of the root mean square speed. So this is for the relationship between the pressure and the speed. Now we consider the translational kinetic energy of the molecule. This is another problem. We consider a single molecule of an ideal gas, and it has speed changes when it collides with other molecules. Okay, before we do not consider the collision between molecules. Now we consider the collisions between, now this is between molecules. We can calculate the translational kinetic energy of this single molecule at any constant, right? You remember that the kinetic energy can be written as this one. Các bạn nhớ công thức đúng không ạ? Tính động năng. And if we want to find the average translational kinetic energy over time of this single molecule, because the kinetic energy will change over time, okay? What we consider is the average translational kinetic energy. Then we will have this one. We just replace it with the average speed. The average speed here. This is actually the root mean square speed squared once again. This one. Good. And because we know the expression of the root mean square speed, we rewrite it here. We rewrite it here. Is it okay?
Yes.
We continue. Now we continue to substitute the root mean squared speed here. We did it already, and the number of the gas constant. We can express the translational kinetic energy like this one. This is, remember, this ratio R over NA is actually the Bosman constant. Then you can rewrite the translational kinetic energy as an expression of the Bosman constant. Then at a given temperature T, all ideal gas molecules, no matter what their mass, they will have the same average translational kinetic energy. They have the same, okay? It depends, the translational kinetic energy depends only on the temperature. If you look at here, the kinetic energy depends only on the temperature. So when we determine the temperature of your system, you also determine the translational kinetic energy. Good. We try to finish the mean free path then. Yeah. Then I think if we can stop here or we continue to study a new concept, the mean free path. The mean free path. What is the mean free path? If we consider a molecule, okay, this molecule will move through the gas, okay, and it will change both speed and direction when it collides with other molecules. For example, this one, it will travel until here, it will collide with this one. When we consider that the collision is elastic, then, for example, this molecule will change the direction. Okay, change direction, and also the kinetic energy. This one will also change the direction and kinetic energy, but the total kinetic energy and momentum are conserved. Okay, this is for the elastic collision, but the direction will change, the kinetic energy will change. Of course, between the collision, because we already eliminate the force, the interaction between two molecules, then between the collisions, the molecule moves in a straight line. And we consider that this speed is constant. Okay, the path from here to here is constant speed, here to here is constant speed. Of course, the speed here should be different than the speed here. But during the collisions, we assume that speed is constant. What we want to study is called the mean free path. This is defined as the average distance traversed by a molecule between the collision. Okay, the average distance traversed by a molecule, yeah, between the collision. For example, this molecule, it collides here, it changes here, so the distance here should be different than the distance traveled here. So what is the average distance traveled by this molecule between the collision? This is what we want to study. How to do so? Now, if we consider that this is the molecule that we want to study, this one moves, and this one will stay. Okay, for now, okay, only for now, we consider that this one moves and this one will stay. There's a collision. Okay, there's a collision. When the centers of the two molecules come within a distance d of each other, with the d, the molecular diameter. So please look at the figure A. Like this, we have a collision. Okay, do you understand until here? If you do not understand, please stop me, okay? This is the case when we have a collision. When the centers of two molecules come within a distance d of each other. Good. Then if we find, to simplify the problem, if we find an equivalent representation of this case, we can consider that a big molecule which is actually moving. And this big molecule, this time it has a radius d and a diameter 2d. All the molecules here, all the molecules, we can consider as a point only. Then now the problem from this one, when we consider two separate molecules, we will consider only one big molecule. Okay, we consider one big molecule. The condition for a collision is unchanged. What are we going to do with this big molecule? Once we already define this molecule, okay, we consider the distance traveled by this big molecule over the time delta t and speed v. So the product of v delta t is actually the distance, right? The distance that the big molecule can travel. Okay? So during the time delta t, this big molecule can sweep out a cylinder of length v delta t. And this cylinder has a radius d. So this is the radius of the molecule, right? A diameter d, this one, because this is the diameter of the molecules. And the volume here is actually this one times this one times the area p d squared times v delta t. Do you agree with me? So this is the volume of this cylinder. The volume, okay? Now the number of collisions that occur in time delta t, the number of collisions I'm talking about, is then equal to the number or the point, okay, to the number of molecules that lie within this cylinder. Okay, the number of molecules that lie within this cylinder, we can simply determine this number. So the number of molecules in a cylinder, in this cylinder, is actually the number of molecules per unit volume. This one. So N over V times the volume. Đúng chưa? Nếu mà chúng ta định nghĩa như này không bao giờ sai này. Số phân tử trên một đơn vị thể tích nhân với thể tích thì sẽ ra số phân tử của trong cả cái xi lanh này, đúng không ạ? So remember, please, once again, write it down. So here we have the number of molecules in the cylinder. This is also the number of collisions that occur in time delta t. Good. If you are able to follow until here, then you should be able to determine the mean free path. So lambda. Actually, the mean free path is the ratio between the length of path during the delta t, the length of path during the delta t, over the number of collisions, okay, in delta t. the length of path during delta T over the number of collisions in delta T. Here, remember once again, we consider only for one molecule. We consider only for one molecule. If we rewrite it for one molecule, okay, this will become, okay, the length is this one. The number of collisions is this one. We just established the expression. Then we can rewrite it like this one. Okay. This will be gone and this will be gone. Now, please be careful. This equation, when we establish it, we assume that all the molecules except the one we are considering, they are all at rest, right? They are all at rest. But actually, this is not true. In reality, all the molecules are moving. Then we should consider this movement into our expression. How to do so? Here, we should rely on the mathematics. Now, how to consider it? If we consider it, sorry, we see that there are two things that we have cancelled, the speeds. But actually, if we consider the movement, yeah, we consider the movement of all the molecules, we see that in the numerator, is the numerator, this one, okay, is actually the mean speed of the molecules. Mean speed of the molecules relative to the container. Good. Meanwhile, when we talk about the collisions, the number of collisions, the speed here is the speed, the mean speed of our single molecules relative to the other molecules. Ok, một cái khi mà chúng ta ở cái tử số này thì nó là cái vận tốc trung bình đối so với cái container của chúng ta. Thế nhưng mà khi mà chúng ta xem cái va chạm này, cái số lần va chạm ở đây thì chúng ta lại phải tính cái vận tốc, đó là cái vận tốc tương đối. Vận tốc tương đối giữa cái hạt mà chúng ta đang xem xét cái chuyển động với cái vận tốc của cái hạt khác. Đó, bởi vì thằng khác nó cũng chuyển động. Thế thì lúc này thì ta sẽ có một cái vận tốc tương đối giữa hai hạt chuyển động với nhau. Đó, thì các bạn bắt đầu thấy là hai cái vận tốc này nó khác nhau khi mà chúng ta xem xét là tất cả các cái phân tử khác nó cũng chuyển động. Good. Then here I remind you a little bit of mathematics, how to determine the relative speed between two molecules. For example, I have the molecule 1, I have the molecule 2, but each molecules has random molecular velocities. Then the relative speed between the two molecules can be written as this expression, the vector v1 minus vector v2. Cái này là toán vector nhé. Không biết các bạn học chưa? Các bạn học chưa? Trong algebra hay là trong gì đó? Bạn nào học chưa?
Học rồi sao? Algebra.
Okay.
Linear, trong linear.
Oh, okay. Then you can develop this expression. This can be written like this. Cái này là toán nhé. Các bạn nhớ rồi, bạn có thể. So you can develop it. This is actually this one. Okay, but for random molecular velocity, so the product of two randoms, okay, molecular velocities will equal 0. This one equal 0. Then you can rewrite the relative speed as this expression. Okay. Here, when we consider that the speed is similar, is constant and similar to each other, then we can write the relative speed equal to root mean squared of 2 and an average speed. So the relative speed can be written like this. If we now replace this expression to what we have written, then we should have this one. Okay. If we rewrite the formula, we should have this one. And the difference is the root mean squared of 2 here. This is the main difference. Before we do not have this one. And this is the final formula of the mean free path. From now on, if you like, you can just have to remember this formula. But you should also understand the way, we find it. You should also understand the way we find it. Is it okay until here? If we consider, for example, the air molecules, so at sea level, it will have a mean free path, which is very small. So if we look at the mean free path, we can have a very good idea about the density of the gas. Here we see that it has a quite big density for the air molecules. At a very high height, then we see that the mean free path, so I mean the distance that the molecule can travel before colliding with other molecule, is becoming bigger. And at a height of 300 kilometers, then you see two molecules of air will have a very big distance already of 20 kilometers. So mostly we have no air anymore. Okay, mostly we have no air when we go high. I will try to upload. We will see the exercise each other once again. We try to calculate the mean free path of oxygen. Okay, so for the first, we calculate the mean free path for oxygen molecules at 300 kelvins and atmospheric pressure. Atmospheric pressure. Cái này là 10 mũ 5 nhé. Tôi chưa sửa, một tí tôi sẽ sửa và tôi sẽ upload. I will upload. I will fix some error here and then I will upload the slide on Moodle. Tôi sẽ sửa và tôi sẽ upload cái slide này lên Moodle nhé. 10 mũ 5 Pascal, chứ không phải 10 mũ trừ 5. We consider the pressure atmosphere. Okay. We assume that the oxygen gas is an ideal gas having the molecular diameter of 290 picometer. Then what is the mean free path? We can apply this one. We can apply the formula. Then what we know is the pressure. Then we can change the expression. We can calculate the ratio N over V as an expression of the gas constant and the pressure, the temperature, what we know here actually. Then we should be able to have the final result. Yeah. The Bosman constant is what we know. The temperature is given here. This is what we know. The pressure is what we know. Then we rewrite this ratio. Then we assume the average speed of the molecule is 450 meters per second. We need to find the average time between successive collisions. We need to calculate the time, okay, for any given molecules. So actually, this is the distance. This one, the mean free path, the average distance divided by the average speed. So it becomes to divide the mean free path to the average speed. Then you should be able to find this result. Is it okay? I think we can stop here. Next time we continue with the distribution of molecular speeds and so on. I will upload it. I will upload my slides right now, and then please take a look, okay, for you to be able to do the exercises. I think tomorrow, I'm not sure, but you should reread it. Yeah, once again, I'm sorry for today when we have to start late because of an unexpected meeting of the rector board, and I had to be present. Yeah, but I think I speed up already, and please reread all my slides once again. And if you have any questions, for example, we can try to, I will answer all of your questions during, for example, during the tutorial class. Is it okay?
Yep.